Hello guys, welcome once more to another video in our YouTube channel. So this video is going to kind of be a little bit lengthy because I'm going to be doing two topics. The first one is to solve a differential equation with initial conditions, and the second question that follows is to sketch a curve. Actually, the two questions are together, all right? So we're actually live on YouTube, and it is a pleasure to have you guys here. If you're joining us for the first time, make sure you like the video, you subscribe to the channel, and you turn on your notifications so that whenever live videos are available, you'll be notified to come and follow. Alright, so if you have a problem while watching the video, you can comment in the comment section and I'll be there to answer your problem. Okay, so whenever you have a problem while watching in any part of the video, just type on the comment section. If you're watching live, good, you can type on the live comment section, or if maybe you're watching later, that is if the video will still be available for you, you can also type in the comment section of the video. Okay, so let's get started. So I'm going to be very detailed in my explanation, regardless of the fact that the video might be long, but I believe that it is very important that you really understand these things. Okay, so the first question says we should solve the differential equation which has been given to us, and we have initial conditions also given to us. So we have to solve the differential equation x plus 2 all squared times dy dx plus 3y squared equal to 0, given that y equal to -2 when x is equal to 0. Okay, so we are going to begin with that part of the question. Okay, all right, so in pure mathematics, you're always going to be given differential equations called variable separable differential equations. These are first order differential equations where we can separate variables and integrate both sides. Separating variables means we take everything that concerns each of the variables separately on the left hand side and on the right hand side. Okay, so I'm just going to copy my original differential equation, then I try to separate variables. So having this original differential equation, what do we do next? The next thing to do is that we have to subtract 3y squared on both sides. Okay, so we are going to have x plus 2 all squared times dy dx equal to -3y squared. Now you realize that I have on the left hand side a function of x together with dx, so I'll make sure I send it to the right hand side. Then on the right hand side I'll just keep this -3 there. Okay, I'll just make sure I send this y squared now to the left hand side so that it meets the dy on the left hand side. Okay, so if we do that, what do we have? We are going to have dy over y squared is equal to -3 dx divided by x plus 2 all squared. So I am done separating variables. You realize that everything that concerns y is on one side and everything that concerns x is on the other side. You could still decide to divide all through by the -3 and you put the -3 down here, no problem. But just to avoid cases of mistakes, I just allow the -3 to stay on the right hand side. Alright, so when I'm done separating variables, the next thing to do is that I integrate both sides. So I integrate dy divided by y squared, and here -3 is a constant, so it is out of the integral. Then I integrate the x over x plus 2 all squared. Alright, so now we have to integrate. So I'm going to recall you some important things about integration. So generally, if you want to integrate, let me say dx divided by ax plus b raised to the power n. Alright, if you want to integrate dx over ax plus b raised to the power n, you can rewrite this as the integral of ax plus b raised to the power -n then dx. You realize that this is a linear factor, ax plus b. Okay, I want to do it so that we integrate the right hand side. Then I'll also give you another rule so that we integrate the left hand side. Okay, alright, so if you want to integrate this will just give you, what you do is that you write the very ax plus b raised to the power negative n plus 1 divided by, you have negative n plus 1. Then you differentiate the ax plus b, and when you differentiate ax plus b, you just have a. Okay, let me take an example. Of course, we need to add a constant of integration because it is an indefinite integral. There are no bounds. Let me take an example. If I say, and remember that this n cannot be equal to 1. So this n that is down here cannot be 1, because if n is 1, you realize that you're going to have here negative 1 plus 1, which is 0, and we cannot divide by 0. Alright, so this happens for n, for any value of n. So for all n different from 1. So any n different from 1, it is going to work. Now let's take an example. If I say integrate dx divided by, let me say 2x plus 1 all squared, you tell me that this is the same as the integral of 2x plus 1 raised to the power negative 2 dx. And by the rule, I'm going to take 2x plus 1 raised to the power negative 2 plus 1 divided by negative 2 plus 1. Then I differentiate the 2x plus 1 to have 2. So this 2 here is a derivative of 2x plus 1. Then we add the constant of integration. So this is just going to give us, now the denominator, this is negative 1 times 2 is negative 2. So I'm just going to put negative half, okay? Then I now multiply it with. Now you realize that this is negative 2 plus 1, which is negative 1. So you're going to have here 2x plus 1 raised to the power negative 1. But 2x plus 1 raised to the power negative 1 is equivalent to 1 divided by 2x plus 1. Then we need to add the constant of integration. So this is just a basic principle, okay? Alright, and remember this works only for linear functions below here. It does not work for quadratic functions. It does not work for quadratic functions again. Alright, so this is just a basic recall I've given you guys so we can use to integrate this these two sides. So I'm going to continue from here. Okay, so having in mind that the integral of, now this left hand side is the same as y raised to the power negative 2 dy. Remember that this y here is also a linear function. It's just that there is no term in, there's no constant, so we do the same thing, equal to negative 3, the integral, I'm going to have here x plus 2 raised to the power negative 2 dx. Okay, now let me just tell you guys that if you want to integrate dx divided by ax plus b, that is if your n is 1, you see in this first condition n is not 1, so in the second condition that n is 1, what we do is that we just take 1 divided by the derivative of the denominator, which is a, then we multiply the result with the ln of the absolute value of the denominator, ax plus b. Then we add a constant of integration. So in the case when n is equal to 1, this is the procedure. For example, if I say what is the integral of dx divided by 2x plus 1, not 2x plus 1 all squared, but 2x plus 1, you tell me that this is 1 over, what is the derivative of 2x plus 1? It is 2. Then we multiply it with the ln of the absolute value of 2x plus 1. Then we add a constant of integration. So these are basic principles that you have to pick up when you're studying integration as a topic, because differential equations is an application of integration. Alright, so in this case, so let's just pick up from here. This is just a basic recall. So let me just try to kind of highlight it, basic recall, so that you don't get mixed up with the recall and the solution. So the recall ends here. Alright, so we continue solving from where we ended. Okay, so next thing to do is okay, so we have rewritten this guy as this. Okay, so we have rewritten it as this. Now let us see what to do. So let us integrate normally. Like I said, we are going to have here y raised to the power negative 2 plus 1 divided by negative 2 plus 1. Then we differentiate the y. Okay, when we differentiate y, we just have 1. In fact, here we are just using the power rule, so we end here. Then we add a constant of integration, maybe c1, because it's an indefinite integral, equal to negative 3 is outside. Now let us integrate what is inside here. So what do we have? Here we have x plus 2 raised to the power negative 2 plus 1 divided by negative 2 plus 1. Then we differentiate x plus 2 just to have 1. Alright, then we add another constant of integration, maybe c2. Okay, so you realize that if you simplify the left hand side, okay, in fact this constant of integration c1 here, we can just subtract it on both sides. So if I subtract on both sides, I'm going to have minus c1. Okay, but c2 minus c1 is a constant because c2 and c1 are all constants. So this c2 minus c1 is a constant. That is why generally we just add the constant of integration to one side of the differential equation. So I'm just going to call it k. You see. Okay, now the left hand side will be simplified. If we simplify the left hand side, we just get y to the power negative 1 divided by negative 1 equal to, if we simplify the left hand side, we have negative 3. Now the denominator is negative 1. Okay, the numerator is x plus 2 raised to the power negative 1. Then now we add a constant of integration k. So I think we can go to the next page. So let's continue from here. So from here, what do we have? Now y to the power negative 1 over negative 1 is just negative 1 over y. Okay, because this y to the negative 1 is 1 over y, then this negative sign is multiplying the 1 over y. Then we need to equate it to, we realize that negative sign here cancels with the negative sign here to give us a positive. We are just left with 3. Now we take 3 divided by x plus 2, because x plus 2 to the negative 1 is 1 over x plus 2. Then we add a constant of integration. Okay, from here I'm going to make y the subject of the formula. Okay, so if we make y the subject of the formula, what do we have? We first of all have or let's see, what can we really do? Anyways, let's just find a constant of integration first before we start making y the subject of the formula. So we go back and take the initial conditions. The initial condition is that given that y is equal to negative 2 when x is equal to 0, we need to find the exact solution. So given that y is negative 2 when x is 0, we need to find the value of k. So I'm going to replace y with negative 2, and we have negative 1 over negative 2, okay, equal to 3 divided by, replace x with 0, 0 plus 2, then plus k. So this means that we have half is equal to 3 on 2 plus k. So what will be the value of k? So k will just give me half minus 3 on 2. Half minus 3 on 2 is negative half, because 0.5 minus 1.5. 0.5 minus, sorry, it's negative 1. Yes, negative 1. So that's the value of k. So since k is negative 1, we are going to replace k equal to negative 1 in the above solution that we have. So if we do that, we are going to have negative 1 over y equal to 3 divided by x plus 2. Then we replace k with negative 1, so that's a minus 1. Then I'm going to find y, because I have to put my answer in the form y equal to f of x. So to get y, I'm going to simplify the right hand side. So minus, in fact I'll divide all through by the minus sign first. So when I divide all through by the minus sign, this first term here picks a negative sign, okay, and then the second term, which is negative, now becomes positive. Now I can rewrite this as starting with 1, okay, 1 minus this is the same as negative this plus 1. Okay, now the LCM is x plus 2. Okay, now we are going to have here x plus 2 minus 3, where we do the LCM. So this is going to give us x plus 2 in the denominator and x minus 1 in the numerator. So actually 1 divided by y is equal to x minus 1 divided by x plus 2. So what is the value of y? We just have to reciprocate. Alright, so y is going to give us what? It's going to give us x plus 2 over x minus 1. So that is our solution. So this is our solution. So remember, to get the value of y, I can just cross multiply. So this x plus 2 goes up here, this x minus 1 goes down, and then y goes up. So we get y to be equal to x plus 2 divided by x minus 1. So that gives us the solution of that differential equation with respect to those initial conditions. The first solution we had with the value of the first solution we had where there was k inside is a general solution, okay, but this is now a specific solution because k has been found using the boundary conditions that were given to us. So this is our solution. Okay, now if we move to the next question, you just realize that the function we have had in the previous question is exactly the function given to us in the next question to sketch. This is very important because if a student is able to have this, it builds your it motivates you, that it means that you are in the right path, because the function you have just had is exactly the same function you have been asked to sketch in the next question. So let's move on to sketching of curves. Alright, so we have been asked to sketch the curve y equal to x plus 2 over x minus 1, showing clearly the point where the curve meets the coordinate axis and the behavior of the curve as it approaches its asymptote. So the first thing to do is we are going to find the domain of definition of the curve. Okay, I'll not be too detailed with the domain because in pure maths, just rational functions will be given to you, and in a rational function is defined when the denominator is not 0. Alright, so this function is y equal to x plus 2 over x minus 1. So this function is defined if and only if, so this function is defined if and only if the denominator x minus 1 is not equal to 0. And this works for all rational functions. Okay, so if I give you a rational function y equal to maybe ax plus b divided by cx plus d, so this function is defined if and only if the denominator cx plus d is not equal to 0. Even if you had quadratic and quadratic or linear and quadratic, once it's a rational function is a function where we have the ratio of two polynomials, all right, and clearly the numerator will always be defined. So for the whole function to be defined, we just set the denominator not to be 0 and find the range of values of x. So in this case, you realize that your x will not be equal to 1. Now we need to write it as an interval. Okay, so we need to write the interval notation of the domain. So if x is not equal to 1, what does this mean? X not equal to 1 is just equivalent to x less than 1 union x greater than 1. So all values that are less than 1 and together with all values that are greater than 1, you cannot be 1. That's why there are strict inequalities. Okay, so I'm going to write this as an interval. So we are going to begin from minus infinity, then we arrive 1, then you continue from 1. Okay, you continue from 1, then you arrive plus infinity. So this is my domain. You see, the boundary values are 1 from below and 1 from above. So if you're less than 1, you begin from minus infinity. Make sure you exclude. Then when we arrive 1 also, we also exclude. Okay, then we continue from 1, then we also exclude the 1. All right, then we arrive plus infinity and we also exclude. Okay, so this is my interval notation of my domain. The next thing to do is that we need to find the limits at the boundaries or at the bounds of the domain. Okay, I wrote this interval notation of the domain so that we can easily get the bounds. The bounds are negative infinity, 1 from below, 1 from above, and positive infinity. So let's go. So we are going to find the limit at negative at plus or minus infinity. So I've just generalized the limit as x tends to plus or minus infinity of y, that is of x plus 2 divided by x minus 1. So let me also generalize it here. So if we have a rational function like this, okay, and you want to find the limit as x goes to plus or minus infinity, so the limit here as x goes to plus or minus infinity of ax plus b divided by cx plus d is just equal to a over c. That's a general case. There's no need to be proving it. Anyways, let me just try to prove. Alright, but at the end of the day, you are not actually supposed to be proving, but though it is essential, but let me just try to do it. So if you want to get this limit, what you do is that you go to the numerator and divide all through by the highest power of x. The highest power of x in the numerator here is x, just x to the power 1. If there was x squared, you divide each term by x squared. So I'm going to divide ax by x, and I'm going to divide b by x. I'll do the same to the denominator so that it remains the same. So I'm going to divide the highest power of x in the denominator here. In fact, if I'm dividing by x, it's like I'm factoring out x, okay? Because if you're factoring out from something, the result is just a division. So if I factor out x from ax, the answer is just gotten by taking ax divided by the x. So the x is outside. If I multiply the x, this x outside here, with the ax on x, I'm going to be left with ax. If I factor out x from b, the result is b over x. So that if I multiply the x with the b over x, I get b. Now I'm also going to factor out the highest power of x in the denominator, which is x. Now if you factor out x from cx, the answer is cx on x. If you factor out x from d, the answer is x on d. So this is going to give us the limit. Now the numerator, you see that the x in the numerator cancels with the x in the denominator. So you are going to have here a plus b over x. Alright. Then here you're going to have the same thing, c plus d over x. Alright. Now as x goes to plus or minus infinity, this quantity here goes to 0. So that quantity goes to 0. This quantity also goes to 0. Okay. And if those quantities goes to 0, the resulting answer will just be a over c. Alright, because the answer is just going to give us a plus 0 divided by c plus 0, which is a over c. So in essence, this is because they are linear functions. If the degree of the denominator was higher than the degree of the numerator, the result will give you 0. Let me take for example, I'm just making it detailed so that it's going to help in other questions. Imagine that we want to find the limit as x goes to plus or minus infinity of a linear function over a quadratic, maybe cx squared plus dx plus e. We do the same thing, alright? What we do is that we go to the numerator and factor out the highest power of x. So if you do that, you just have x here, you'll be left with a plus b over x, alright? Now in the denominator, we factor out what? X squared, because that's the highest power of x. Here we are going to be left with c. Then we are going to be left with d over x, because so that when you multiply x squared with d over x, you have dx, and here we're going to have e over x squared. So that's what we have. So finally, what do we have as a limit? So you have here, you have this x divided by x squared is 1 over x. So I just cancel what is there and I put x that is here. Alright. Now you see that as x goes to infinity, this man goes to 0. Okay, because if x is becoming large, its reciprocal vanishes to 0. This everything here also goes to 0. So c over d over x goes to 0, e over x squared goes to 0. So our final answer is just equal to, you realize that the numerator will be going to a and the denominator will be going to c times x. Then we need to put a limit. So it is a limit. So we have sorry about that. So it gives us the limit. Now our numerator basically goes to a because b over x goes to 0. Our denominator basically goes to c times x, okay, because everything here goes to 0. So at the end of the day, since a and c are constant, you can pull it out of the limit. So we have a over c. Now when you have a over c, we are going to be computing the limit as x goes to plus or minus infinity of 1 over x, which gives us 0. So we are going to have a over c times 0, okay, which is going to give us 0. So you see that when the degree of the denominator is higher than the degree of the numerator, the answer is 0. If they have the same degrees, if here was also quadratic, the answer is just going to be the ratio of the coefficients of the highest power of x in both. So if here was ax squared, my answer would be a divided by C. Okay, so these are just some little basic things that you really have to know so that it saves you time in the hall, especially in paper 1 as well. Okay, so let's come back to what we have. Let us come back to where we were. So the limits are the boundaries of the domain. So by the explanation, you see that the coefficient of x here is 1 and the coefficient of x in the denominator is also 1. Okay, so at the end of the day, what will be the limit is going to give us 1. At plus or minus infinity, we have 1. Now we need to find the limit as x tends to 1 from below. Below means that you are less than 1. You see, in this interval here, you are less than 1. And above means you are greater than 1. In this interval, you are greater than 1. Be very close to 1 though. Alright, so we also need to find, now let's get the limit as x tends to 1 from below. So the limit as x tends to 1 from below, that's 1 minus of x plus 2 divided by x minus 1. What does this give us? Now here we have to kind of replace, okay, a number that is less than 1 from below is a number that is less than 1 but very close to 1. So we can take 0.999999. Now if we take the 0.9999 and we add it to 2, what are you going to have? You are going to have 2.99999. Now if we take the 0.999 and we take minus 1, it's going to give us a negative number, negative 0 point something. Okay, so you realize that the result will be going to negative infinity. Here your calculator can do the job. All right, your calculator can really do the job for you so that you really get it. So just take 0.999, just fill your calculator with all the 9s, replace in the numerator, replace in the denominator, and simplify. You realize that the answer will be a negative, very big number that is approaching negative infinity. Now if we also do the limit, if we now do the limit as x approaches 1 from above, so 1 plus. Now 1 from above is a number that is greater than 1, but very close to 1. So we can take maybe something like 1.000001. You see, this number is very close to 1, but it is bigger than 1 because it is ending with 1, it's not ending with 0. So if you replace it here and subtract, you're going to have 0.0000. In fact, just replace and you realize that the result will just give you a positive big number. So that's positive infinity. So in these cases, your calculator really does the job for you. So we have gotten the limit at the boundaries of the domain. Now the next thing to do is we have to talk about the asymptotes. All right, the asymptotes. Now what are asymptotes? Asymptotes are lines that behave like the curve at infinity. So in pure mathematics, we have 2 types of asymptotes. We have the vertical asymptotes, which by definition, if x is equal to a is a vertical asymptote, then we have that the limit as x tends to a of the function f of x is equal to plus or minus infinity. That is the definition of a vertical asymptote. Alright, but normally a short trick is that to get a vertical asymptote, just come to the function and equate the denominator to 0 and find x. It is different from the domain. The vertical asymptote, a shortcut to get it in pure math is come to the function, equate the denominator to 0 and find the value of x. The value of x is your vertical asymptote. Alright, that is for pure math. I'm specifying because it doesn't happen like that in further math. Because in further math, sometimes you can have a function that doesn't have a denominator. So what are you going to do? So in pure math, the trick is that just equate the denominator to 0 and find all the values of x. All those values of x gives you the vertical asymptote. Or you can just take it directly from your limit. We have realized that the limit as x is tending to 1 from below and 1 from above, you are still turning to 1. It's giving us plus or minus infinity. So x equal to 1 is a vertical asymptote. Or if you want to use a trick, just come here, equate x minus 1 to 0 and find x. X will give you 1. So we can deduce that from the limit, that x equal to 1 is a vertical asymptote. Now let's talk about horizontal asymptotes, and that will be all for maths. So horizontal asymptote. So horizontal asymptote is gotten by the limit at plus or minus infinity. So if y is equal to b is a horizontal asymptote, then we have that the limit as x goes to plus or minus infinity of our f of x will be equal to b. B is a real number, okay. Horizontal asymptote means that a line that is perfectly horizontal, and a line that is horizontal is in the form of y equal to something. A line that is vertical is in the form of x equal to something. So this a here is a real number, alright, and this b is also a real number. So when the limit at plus or minus infinity of a function gives you a real number, that real number is a horizontal asymptote. So by definition, you realize that we can deduce that since the limit at plus or minus infinity is giving us 1, it means that y equal to 1 is a horizontal asymptote. So we can deduce from the limit that y equal to 1 is a horizontal asymptote. Okay, so what's the next thing to do? The next thing to do is we now need to talk about the monotony of the function. So all important points are in red. So let's now talk about monotonicity of the function. So here we talk about the turning points, we talk about where is a function increasing, and we talk about where is a function decreasing. Okay, so the first thing to do is we find dy by dx. That's the first thing. So y is equal to x plus 2 over x minus 1. Now let us find dy by dx. So dy by dx, we are going to use the quotient rule. Okay, the quotient rule says that we keep the denominator, which is x minus 1, we differentiate the numerator, which will just give us 1, minus, we now keep the numerator x plus 2, and we differentiate the denominator, we have 1. Then we divide it by the square of the denominator. So that's the quotient rule. So it is v du minus u dv over v squared. So if you simplify, you are going to have the x minus 1. Then let's subtract x minus x plus 2. So we multiply every term by negative. So it will be minus x minus 2. Then divided by x minus 1 all squared. So it therefore means that, in conclusion, our dy by dx is equal to, now x minus x is 0, negative 1 minus 2 is negative 3. So we have negative 3 divided by x minus 1 all squared. So that is the value of dy by dx. Now let's talk about increasing. So let me just give you some 3 conditions. If f prime of x is equal to 0, then x is constant. Then f is constant, so the function is not moving, it's constant. Now the next thing is that if f prime of x is greater than 0, then f is strictly increasing. Okay, and the next thing is that if f prime of x is less than 0, then f is strictly decreasing. But if there was an equality here, we are going to say increasing only, or monotonic increasing. But if there's an equality here also, we also say just decreasing. But when there are strict inequalities, we also say strictly increasing or strictly decreasing. So we now have to come to the function and we look for the sign of the function. Okay, now you realize that just by observation, the denominator of this function is always positive. Now if f prime is equal to 0, then f is constant. That is, we need to find the stationary point or the stationary point. Because there's a difference between stationary points and turning points. So this one is the definition of stationary points. Okay, so for a ratio to be 0, we just need that the numerator is 0. But since the numerator is not 0 here, it means that turning points will not exist. Alright, so the function will be if the turning points don't exist, it means that the function is either only increasing or only decreasing. Because for you to be increasing and decreasing, you must have a turning point where you're going to increase and arrive, then decrease from there, or you decrease and arrive and then increase from it. But since we have realized that the numerator of this dy x is not 0, it therefore means that there were no turning points. Now let us look for the sign of f prime. Okay, now by observation, x minus 1 all squared is always positive, because even no matter the value of x, even if this x minus 1 here is negative, once we square the result will be always positive. Now this 3 here is also positive, so it means that this portion here is positive, but now there is a final negative sign. Okay, so what I'm going to say is that for all values of x in the domain of my function, we know that x minus 1 all squared is always positive. Okay, because it cannot be 0, because for it to be 0, we need that x is 1. The 1 is not in my domain. My domain says x is not 1. So x minus 1 all squared is always positive. So it therefore means that if I take a positive number 3, so if I take 3 and I divide it by a positive number x minus 1 all squared, the result will also be positive. Alright, now but there is a negative sign that is here, so I'll multiply both sides by negative. So if I multiply both sides by negative, I'm going to have that negative into negative 3 over x minus 1 all squared will be what? Less than 0, because I've multiplied by negative, so the inequality sign will reverse, which is just telling us that my dy by dx is always negative. And if it is always negative, it means the function is always strictly decreasing. Very important. Alright, so this means that, so we can conclude that therefore dy by dx is less than 0. Hence, the function y equal to x plus 2 over x minus 1 is always strictly decreasing on its domain. Alright, so this is the monotony of the function. Alright, okay, now the next thing to do is let us try to get the intercepts. Okay, then we now draw the variation table. So let's talk about the intercepts. So intercepts. So the intercepts will be on the x-axis and on the y-axis. So when x is equal to 0, we need to find the value of y. Y will just give us 0 plus 2 divided by 0 minus 1, which is negative 2. Hence, the first intercept I is x equal to 0, y equal to negative 2. Now, when y is 0, when y equal to 0, we need to find the value of x. It means that x plus 2 over x minus 1 is 0. So if you cross multiply, we just have that x is equal to negative 2. Hence, another intercept will now be when x is negative 2, y is 0, or when y is 0, x is negative 2. So I have two intercepts, 0, negative 2, and negative 2, 0. Okay, now the last thing is the variation table. Alright, variation table. Now, the variation table, or in fact, let me just sketch. Yes, let us try to see if you can sketch without the variation table, but I think it's important to also give the variation table a very important. But I'll give you the sketching. Yes, let me see if we can sketch without the variation table. So here on my coordinate axis, I have the x-axis and the y-axis. I think I'll be a little bit slow here because I have to insert shapes. So here we have the y-axis and we have the x-axis down this way. Now the first thing to do is I indicate my asymptotes. Alright, let's go back. How many asymptotes do we have? We have two asymptotes. X equal to 1 is vertical, y equal to 1 is horizontal. So what I do is that on my coordinate axis, I try to calibrate, sorry. So this line is passing through x equal to 1, alright, and then it is kind of, it is a dotted line. So, let me just try to increase the thickness, then I give it to be dashes. So that is a vertical asymptote, okay, and I'm going to label it x equal to 1. So x equal to 1, that's my vertical asymptote. So this x it is passing through x equal to 1 on the x-axis. Okay, so that's my vertical asymptote. Now horizontal asymptote will pass through y equal to 1. So maybe I'm just approximating that this could be y equal to 1 here. Okay, so that's for horizontal asymptote. We increase the thickness and we give it dashes because it's an asymptote. Okay, so that is for y equal to 1. Still, it's a horizontal line passing through 1. Okay, now next thing is my intercepts. I have two intercepts. When x is 0, y is -2. So I go and look for the point 0, -2. It's on the y-axis. So 0, -2 could be maybe somewhere down here. Okay, 0, -2 could be somewhere here, for example. So that is my first intercept. Then the next one is -2, 0. That is when x is -2, y is 0. So it's going to be on the x-axis, maybe somewhere here. This is just an approximation. So we have all of this. Then without the variation table, how do you come out with your graph? You must kind of look at your monotony. The function is always decreasing, but your variation table will really help you to know how it actually decreases. Okay, but without the variation table, we'll just try to give a little sketch of the graph. Okay, because from here I already see how kind of the graph is going to look like. So what happens is that the way it's going to look like is going to be like it's going to come down like this. Okay, it's going to come down like this, and then it's also going to come down like this because it's decreasing in all intervals. So what's happened is that, let me just try to draw. So it's going to come down like this. It goes, gets the x-axis at this point, gets the y-axis at this point, and then continue going down. Not really smooth. It's not really smooth. Let me try to do it again for the last time because we don't have time. So it comes down, follows the asymptote, comes down, gets the x-axis, gets the x-axis at the point here, comes down again, gets the y-axis at another point, then now follows the asymptote and goes down perfectly. Okay, so yeah, something like this. All right. Oh, in fact, I'll just put any curve there. Okay, but I think, or let me put it up this way. I'm just trying to draw something. I'm going to change the position of those asymptotes, of those intercepts. So I'm just going to put this point here, all right, and then put this other point here, just to make it to be nice. Okay, now the other curve is now going to be in the other side, so it's going to come down like this, come down. In fact, it is decreasing, so it comes down, and then decreases. So something like that. Okay, so this is just a sketch. All right, this is just a little sketch. I'm not really smooth because I'm using a computer. So this is how my graph is going to look like. All right, that's how my graph is going to look like. So let us try to come out with a variation table. Okay, when we get the variation table, they will actually have to interpret it on the graph, and you see how to always come out with a graph. But it is preferable to get the variation table first before drawing the graph. Okay, so in the variation table contains the domain of definition. So it contains a domain of definition. So this is how you place your variation table. In fact, let me just put a table here. So I have the values of x. For my values of x, I will have the bounds of my domain, minus infinity, intercept, -2 is there, then 1 is there, then 0 is there, then plus infinity. So these are the various values. Now we need to look for the sign of f prime and then the shape of f. So for x, what I do is that I put my bounds minus infinity. It's normally supposed to start from minus infinity, then goes to 1, then after 1 it goes to plus infinity. Okay, then within those intervals you have to check your intercepts. Can x be 0? Yes, x can be 0, so you put 0 here. Okay, now next thing is another intercept was x equal to -2, right? X equal to -2. So in fact we need to put -2 first, they will put 0, they will put 1. Voila. So everything up here concerns x. It has to be in order. First thing is you try to put the domain, then now fit within it the intercept values. Now the next thing here is the sign of f prime of x, or the sign of dy by dx. Now in this interval we realize that in fact in all intervals our f prime was less than 0. So in any interval we take, so in this is an interval, okay, the interval from -infinity to -2, your f prime is automatically negative. So since it is one interval, I'm just going to match it, so f prime is negative. Normally when you're drawing you have to put by the sign, like you put the minus sign, okay, just put a minus sign. Now in the interval 0 to 1 it is also negative, okay, so it is also negative. And then it's also negative in this interval. Then in the interval 1 to plus infinity it is also negative. How will I put it now? Wait. So in the interval 0 to 1 is negative. In the interval 1 to minus infinity is negative. Okay, let's just see what we can do. Okay, so in the interval 1 to minus infinity it is negative. Alright, so I'll just put negative there. I'll just put a negative there, because normally, yeah, something like that, because after 1 you see, in fact, yeah, let me just put it like this. Yes, in this interval it is also negative, okay, it is also negative in this interval. Okay, now the next thing to do is the shape of f, okay, the shape of f. How will f look like? How will f look like? So in this case we said that if f prime is negative, f is decreasing, okay, so f is going to be decreasing. So f, in fact, f is decreasing in all intervals, right? F decreases in all intervals. So it means that since it's decreasing in all intervals, this is what we are going to do. What we are going to do is we are going to put an arrow that shows that it is moving downwards, okay? That's what we are going to do. So what I do is that since it is decreasing in all intervals, it means that in this interval it is decreasing, okay, decreasing here. In the next interval, in this interval it is decreasing. In the next interval it is also decreasing, and in the last interval it is also decreasing. This last interval is from 1 to plus infinity. I don't just want to put the 1 here so that I should not be confused, because the two ones are the same, okay. Let me just put it. All right, now next thing is, okay, you decrease from where to where? You decrease from the limit at minus infinity right down till the intercept, okay, which is f of -2. Now what is the limit at minus infinity? The limit at minus infinity is clearly equal to, let's go back, the limit at minus infinity is 1, okay, so you decrease from y equal to 1. So you're going to decrease from y equal to 1. Let me just try to use this one here. So the curve decreases from y equal to 1, okay, so it decreases from y equal to 1. Well, no need to put y, let's just put 1. So it decreases from 1 right down to where? Right down to f of -2. What is f of -2? It is 0, because that is an intercept, alright? F of -2 is 0. So it decreases from y equal to 1 right down to 0. Then you continue decreasing from 0. Okay, you continue decreasing from 0, because when we leave 2 we still continue with 2. So you continue decreasing from 0. You continue decreasing from 0 right down till you continue decreasing from 0 right down till, wait, there are two things here. we first of all have an interval from, we have the interval from minus infinity to minus 2. Then we have the interval from minus 2 to 0. Alright, then we have the interval from 0 to 1, and then the interval from 1 to plus infinity. So when you decrease from minus infinity to minus 2, you continue decreasing from the minus 2 right down to f of 0. Okay, so when you decrease from minus infinity to when you decrease from 1 to 0, that's for y, you continue decreasing from the 0 right down till when x is 0, y is negative 2. Okay, so I don't know how I'm really going to put it. Anyways, I think I'll do a different video explaining the variation table, but this is just it. You decrease from y equal to 1, that's a horizontal line. You go down till f of negative 2, which is 0. You continue from the f of negative 2 right down to f of 0, which is negative 2. You continue again from there right down to the limit at 1, which is negative infinity. The limit at 1 from below was negative infinity, right? If you check very well, you realize that the limit at 1 from below was negative infinity. So you check the graph, it corresponds. Then after the 1, you now start with the interval 1 to plus infinity. So from 1, this is now 1 from above. The limit at 1 from above is plus infinity. So it decreases from plus infinity right down to where? To the limit at plus infinity. And the limit at plus infinity is 1. Because the limit at minus infinity and the limit at plus infinity are all the same. So that speaks well about our graph. Alright, so if you watch us till the end, if you watch the video till the end, I want to thank you so much for sticking to the end. If you have a question, the comment section is open for you, like I said from the beginning. Okay guys, see you guys in the next episode of Live on YouTube. Thank you for watching and see you in the next video.